Hi students, welcome to Year 9 Science and Unit 1 on atoms and stuff. This is video number 4 and we're going to just be looking at how we apply some of the theories that we've been discussing. So what you want to be able to do is to relate the theories that we've looked at both in terms of particle theory and also kinetic theory to phenomena such as changes of state, the properties of different materials, and also to different chemical reactions. Now that's a lot of things for us to look at, and so what we might do is take one particular phenomenon and see if we can apply what we know about particle theory and kinetic theory to see if we can explain that phenomena. So this is a fairly common occurrence, the setting up of convection currents. That happens both in terms of our weather patterns, but it also happens in things like boiling water, and also turning on heaters and air conditioners and things like that. You get this cycling of warm and cool fluids, and they create these little convection cells. So we can describe them, and of course the key here is the difference between a description and an explanation. So we can describe what's happening in convection currents as follows. You can see that if we have a heat source, what happens with the heat source is the particles directly above the heat source rise, and as they move away from the heat source they start to cool a little bit, and they then move away from that source of heat, where once they're a little bit further away they start to fall, and what will happen is that they will be drawn back in, and so you get these little cycles. That's what convection currents are, and that's just how we might describe them, but that doesn't explain why these particles are moving in these sorts of circular patterns. So are there ways that we can use both our particle theory and our kinetic theory to explain this phenomena? Well, put simply, the particle theory is that all matter is made of particles, and those particles are in motion. So if we think about the water in the pot as being little particles of water, in this case they would be water molecules, then those particles are in motion. Whilst they are linked to one another in a liquid state, they are still capable of sliding past one another, which is one of the reasons why liquids can take on the shapes of their containers. They're not held as rigidly as they would be in a solid, for example, ice. So the particles can move around. The whole of the water itself is made up of individual particles, and while they're attracted to one another, they are also capable of moving past one another. So the particle model does help us to explain how and why particles may be able to do this, but it's not really good in terms of working through the issues associated with the heat. So that heat really needs us to link into kinetic theory. So kinetic theory is the fact that the particles move, and certain properties that we can identify that are associated with the motion of particles is associated with that movement. So when we add heat to any substance, what that does is it increases the average kinetic energy of the particles. Now, because the particles don't become any bigger, that means their velocity must increase. That is, they move faster. And if they move faster, then that starts to get to the heart of what's happening here. So at the heat source, the particles are moving more quickly than other particles around them. And so they basically push through. So the particles that are in the region of heat have on average a little more kinetic energy, so they move more quickly. Once they reach the close to the surface where it's a little cooler, once they reach the surface of the pan, where, or at least where the water and the air interface, they're a little bit further away from that heat source, and so they start to lose some of that kinetic energy. In fact, some of that kinetic energy is actually going to be transferred to other water molecules. Heat, in this case, is conducting. Now, water's not a great conductor, certainly not as good a conductor as some metals, but it does warm up. So we do know that there will be some transfer of heat from those particles that are higher energy, higher velocity, and they will be transferring that energy to other particles. And as they do that, their own overall energy will drop, so their velocity will start to slow down. But because the slower particles are actually being pushed out of the way by the faster moving particles coming from below, they'll be pushed away from that heat source. So fast moving particles are coming up, they're pushing away the slower moving particles, kind of pushing them out of their way. There's nowhere for them to go up. Of course, if they change state, they will, but that would be a different explanation. But assuming that they stay in the liquid, they will be pushed out of the way as the warm particles, the faster moving particles, continue to rise and push them out of the way. As they continue to move away from the heat source, they will lose more kinetic energy. They will start to slow down more and more, and we'll find that there creates a sort of a natural flow as new particles around the area of the heat source are also warming, also increasing in their kinetic energy, and really are being drawn into this center where the heat source is. So what we're trying to do is to link the ideas of particle theory, that all matter is made up of particles, kinetic theory, which is the particles are in motion, and when we add heat to them, they move faster, and that faster motion can change aspects like the temperature, like the pressure, perhaps even the volume. It may well be that the water will expand a little as it's being heated. So all of these are consequences of an understanding and an application of the particle theory of matter and also of the kinetic theory. Remember, the most important thing about our theories is theories are explanations. They're only useful as far as they help us explain experimental observations and data. And so what we want to do is have a look at a few other examples of phenomena that involve chemical reactions, changes of state, or other phenomena, and see if we can use particle theory and/or kinetic theory to help us explain what's going on. So that's an exercise that we'll look at in the classroom. Thanks for watching.